Let us continue the discussion on the change of basis. This time let us look at how the expansion coefficients of a vector change under change of basis. The idea is this: we have a vector, a general ket vector alpha. Now, if you express this ket in terms of the basis, let us say ket A, okay, then we can expand it in terms of AL. Then the expansion coefficients will be what will be the each expansion coefficient? Something like this: AL, bra vector AL, ket alpha. This will be the expansion coefficient. The same vector, if we express in terms of the basis, let us say BK, ket BK, then we get another expansion with a different expansion coefficients. Whenever we change the basis of for the same vector, expansion coefficients will be different. So we get the expansion coefficients something like this: bra vector BK, ket alpha. So it's the same vector. When you change the basis, expansion coefficients will be different. Now the question is, what is the relationship between these two expansion coefficients? These are the expansion coefficients in the new basis, let us say. These are the expansion coefficients in the old basis. How they are connected? Naturally, they are connected through the unitary operator that produces the change of basis. But how? Exactly how? Let us see that. For this, let us start with this ket alpha. First, let us expand in terms of the old basis AL. Okay, so for that we can introduce an identity here and use the completeness condition of the old basis. So we get sum over AL, ket AL, bra vector AL. Okay, this much is equal to identity because of the completeness of the old basis, and ket alpha. So it is just like introducing an identity here and express the identity in terms of the completeness of the old basis. Okay. Now let us take the inner product of this ket alpha with this ket BK. Okay, so we get bra vector BK ket alpha. Okay, that's equal to sum over L. So the bra vector BK will come here. So we get bra vector BK ket AL, then this term AL alpha. Now let us look at this expression. This is the inner product between the old basis and the new basis. Sorry, between the new basis and the old basis. In the previous class, we have discussed the matrix element of the unitary operator U as well as U dagger that produces the change of basis. And you can identify this as the matrix element of U dagger. Okay, the kth matrix element of U dagger. This term. Okay, so this term you can write as, how do we get this is, for example, see what is the kth matrix element of U, operator U? See, AK U AL. This is the kth matrix element of operator U, and this is equal to AK. What happens when U acts on ket AL? When the unitary operator acts on the old basis, you get the new basis BL. Okay, so this type of a structure, bra vector is old basis, ket vector is new basis. This is the matrix element of U. Here the structure is different. Okay, it is the Hermitian adjoint of this one. Okay, bra vector is new basis, ket vector is old basis. Okay, then what you get is the matrix element of U dagger. For example, if we take Hermitian conjugate on both sides, what you get is, on the left hand side, this becomes bra vector AL, U becomes U dagger, and this becomes ket vector AK. On the right side also, these two will be interchanged, so we get BL AK. Okay, so the LKth matrix element of U dagger is BL AK. So here we have BKAL. This L and K are simply dummy indices. We can interchange them. So BKAL. See, look at the structure. the bra vector side you have old new basis, ket vector side you have old basis. That structure is here also. So that means this is the matrix element of U dagger. Okay, which matrix element? This is the LKth matrix element of U dagger. Then this will be the KLth matrix element of U dagger by interchanging L and K. Okay, so this part I can write as what is the KLth matrix element of U dagger in the old basis. Okay, so we have AK, U dagger, AL. Look at this. U dagger will be acting on the bra vector. What happens when U dagger acts on the bra vector? You get this one, the bra vector BK. This is simply like taking the, when U acts on AK, you get BK. Okay, old basis, you get new basis. You simply take the Hermitian adjoint on both sides, then bra vector AK U dagger is equal to bra vector BK. That's what happens here. U dagger bra vector AK is bra vector BK. Okay, and this is AL alpha. Okay, now look at this. What is this term? These are the components of ket alpha in the new basis. This is a column vector. An n by, if it's an n-dimensional space, this is an n by 1 vector. N rows are a single column. So this is a column vector. So this column vector gives the components of alpha in the new basis BK. Look at here. These are the components of alpha in the old basis AL. This is also a column vector. Okay, an n by 1 vector. N by 1 matrix. Whereas this is an n by n matrix, and this is the matrix of U dagger. It's a square matrix, an n by n matrix, because both K and L runs from 1 to n if it's an n-dimensional space. So this is the matrix of U dagger in the old basis. Okay, so we can say this in words. We can say coefficient of ket alpha in the new basis, okay, is equal to U dagger times coefficient of ket alpha in the old basis. So this is how the coefficients are connected. Okay, if you get the coefficients in the old basis, the matrix of coefficients in the old basis, a column matrix, and matrix of coefficients in the new basis, they are connected by the matrix of U dagger. Okay, so that is the relationship between the coefficients in the old basis and the coefficients in the new basis, where this U dagger is the Hermitian adjoint of the unitary matrix that produces the change of basis. We know that the matrix producing the change of basis is sum over K. The structure is the ket side gives the new basis, that is BK, and the bra vector is the old basis AK. So this gives the transformation from the old basis AK to the BK, and whereas the coefficients are connected by U dagger. Suppose we have an operator X. Okay, if we use the basis, let us say ket, ket AM, let us say, then its matrix elements are, let us say, M, X, A, where M and N runs from 1 to some capital N, where capital N is the dimension of the vector space. So this is a matrix element of this operator in the old basis. Now in the new basis, let us say this is the basis BK, ket BK, B1, B2, B3, etc. Suppose the matrix elements are BK, X, BA. K and L are dummy indices running from 1 to capital N. Again, the dimension of the capital N is the dimension of the vector space. So these are the matrix elements of the operator, same operator in the old basis. These are the matrix elements of the same operator in the new basis. What is the connection between the two? how they are related. So we can show this like this. Let's start with this BK X BL. Now here on either side of X, let me introduce identity, and I am using, then I will substitute for this identity the completeness condition of the matrix element, the base vectors of all the base vectors. Okay, so let us do it like this. Okay, so get BK, let us say identity X, here also identity BL. So the idea is to express X in terms of, to rewrite this in terms of the matrix elements of X in the old bases. Okay, for that we have to introduce old bases on either side of X. Okay, so that's equal to, so let me use one index for this side and the other index for this side. Let me use M for this side, N for this side. So we have a summation over N, another summation over N. Then this bra vector BK is there. Then for this identity, let me use the index M. We are using the completeness condition for the old bases. Okay, so here we have ket AM bra vector A. Okay, so sum over M ket AM bra vector AM is identity. Then, so this is for this identity. Then this operator X is there. For this identity, again use the completeness condition of the old basis using a different index N. So we have ket AN bra vector AN. Again sum over N ket AN bra vector AN is identity because of the completeness condition of old basis. And one more factor is there, this ket BL. So this is the matrix element of X in the old basis. To obtain this only, we have introduced identity on both sides and used the completeness condition of the old basis. Now we have a factor here, another factor here. Okay, we can express this in terms of the unitary operator for change of basis. Look at this. The structure here is, on the bra vector side we have old basis, on the ket vector side we have new basis. Okay. Now this quantity is the matrix element of unitary operator U. Okay, which matrix element? Nth matrix element. Okay, that is this in the old basis. Okay, so that is AN U AI. This you can write as bra vector AN. What happens when U acts on AL? You get BL, new base vector BL. So this, whenever you have a structure like this, on the bra vector side old basis, on the ket vector side new basis, it means it is the matrix element of U. Whereas you look at here, on the bra vector side you have new basis, on the ket vector side you have old basis, adjoint of this one. Okay, this is the matrix element of U dagger. Okay, which matrix element? Kmth matrix element. Okay, that is this one in the old basis again, AK U dagger AM. Okay. This will be, when U dagger acts on AK, you get BK and AM, like this. So, sum over N, here I can write AK U dagger AM. This is the matrix element of X in the old basis, AM X AN. And this is the matrix element of U, that is nth matrix element, that is AN U AL. Okay, so what you get here is the matrix element of X in the new basis is equal to the product of the matrix element of U dagger in the old basis, the matrix element of X in the old basis, matrix element of U in the old basis. So if you write this in matrix notation, let us say left hand side is X prime, the matrix element of X in the new basis is equal to U dagger, this is the matrix of U dagger, and this is the matrix of X in the old basis, and this is the matrix of U in the old basis. So X prime, that is the matrix of X in the new basis, this is called X prime, is equal to these are all U dagger, the matrix of U dagger in the old basis, in the matrix of X in the old basis, matrix of U in the old basis. On the right hand side, we have completely expressed in terms of old basis. So X prime equal to U dagger XU. This is how an operator changes during change of basis. Okay, U dagger XU. The new matrix element is obtained like the matrix element of U dagger, and the new matrix element of operator in the new basis. The matrix element of operator in the new basis is obtained as matrix of U dagger in the old basis, matrix of X in the old basis into matrix of U in the old basis. So in short notation, X prime is U dagger XU. This is called a similarity transformation. Okay. So an operator undergoes a similarity transformation under change of basis. And when what is the operator that is producing this similarity transformation? U. And the similarity transformation, the operator that produces this similarity transformation is a unitary matrix. Then this similarity transformation is also a unitary transformation. Okay. So under a change of basis, an operator undergoes a similarity transformation. That is the idea. Or in this particular case, the matrix of producing similarity transformation is a unitary matrix. So this is also a unitary transformation. Now, trace of an operator means an operator is represented by a square matrix. So trace of an operator is the same as trace of that square matrix. That is sum of the diagonal elements of the matrix corresponding to this operator. That is we can say trace of an operator X is sum over n, let us say an x an. These are the matrix element of X in the basis an. So this is a trace. Okay, these are the diagonal elements because the row index and column index are the same, nth element. So sum of such diagonal elements is the trace. Now in change of basis, there is an important result that trace of an operator is invariant under a change of basis. Whenever you make a change of basis from, let us say, ket an to ket bn, then the trace will be the same. Let us try to prove this. So the result is this: trace of an operator is invariant under change of basis. Okay, so let's try to prove this. So there are different ways to prove this, and I am attempting one way. So let us consider trace in the old basis. Okay, so sum over n an x an. Now let me express the same operator in terms of the new basis. So for that I will introduce identity on both sides. And for each identity, I am going to introduce the completeness condition of the new basis. Let us say the new basis is ket b. Okay, ket bk. So this is equal to sum over n. Let us say sum over m, sum over some l. Okay. So we have this bra vector an, and there will be identity on both sides of x. For the identity on the left side, let me introduce. Use let us say m. Okay, so ket bm bra vector bm. Okay, sum over m ket bm bra vector bm. This is the completeness for this is equal to identity because of the completeness of the new basis. And then there is x operator, and there is an identity on the right side also. Okay, just like we have done in the previous previous situation. And for this identity, let me use the completeness of B basis in terms of the index L. So we have bra vector BL, sorry, ket BL, bra vector BL. Okay, sum over L, ket BL, bra vector BL is identity because of the completeness. And then this ket AN is there. Okay, right. Now this is equal to sum over n, sum over m, sum over l. Let me take this term to this end. Okay, this inner product to this end. So we have bra vector BL, then ket AN, then this one. What is this? Bra vector AN, ket BM, then this matrix element BM X BL. Okay. Now here, look at this. You look at this one. You have a summation over n here, and you have a ket AN bra vector AN. Okay. This summation over n ket AN bra vector AN. This is the completeness condition of the old basis. This basis. Okay. And this must be equal to identity. Okay. So we can put an identity here. And the summation also will go. So we have sum over m, sum over L, and then bra vector BL. If this is identity, then this two has gone. Then you have ket BM here. Okay. Then BM X BL. But what is this? This is the inner product between two two ket vectors in the new basis, and they are orthonormal to each other, so this must be delta ML. So one of the summation will go, let us say summation over L will go. So summation over L will go, and what is the only non-zero term? L is equal to M. When L is equal to M, this delta, Kronecker delta will be 1, and you have to put this L also equal to M. So what is remaining is sum over M. We have BM X, this L becomes M, right? So we have BM. So we started with the trace of X in the old basis, sum over n, AN X AN. We ended up with trace of X in the new basis. Okay, so left hand side is equal to right hand side, that means trace of X in the old basis is equal to trace of X in the new basis. That is, trace of an operator is invariant under change of basis. So this is one way to prove it, and this can be proved in another way also. Okay, we know that under change of basis, an operator changes like this: x prime is equal to u dagger xu. This is a similarity transformation or a unitary transformation, and you can show that trace is invariant under unitary transformation. That means you can show that trace of u dagger xu is same as trace of x. This we can prove. So this is also another way, because the u dagger xu is the changed operator under change of basis. So this is the the operator in the new basis. This is the operator in the old basis. So trace of the operator in the new basis is same as trace of the operator in the old basis. That is the idea here. That is what we have proved in another way also. Okay, so you can try to prove this method by this method also. So we have discussed some results under change of basis. So this change of basis is a very important idea in quantum mechanics, where we will be frequently, there will be situations where we will have to change the description from one set of bases to another set, or we have to, another way of saying is that we have to change the representation under one operator, let us say A, capital A, to representation under another operator, let us say capital B. So under this change of representation or change of basis, how vectors behave, how base vectors behave, how a general ket vector behaves, and how an operator behaves, okay, in this type of a situation, and how the coefficients of expansion of the same vector change, and these different aspects that we have discussed in these two classes.